All right, welcome back to another episode of Science with Surbeck. Today, what we're going to be talking about are chemical reactions and balancing chemical equations. So, a couple of objectives I want you to be able to meet by the end of this lesson is as follows. Number one, be able to give general definitions for chemical reactions and chemical equations. Number two, be able to know the steps to balance a chemical equation. And then number three, follow along with examples for conducting chemical or balancing chemical equations. So let's go ahead and get started here with chemical reactions. So chemical reactions are defined as the process by which one or more substances are rearranged to form different substances. Now, a very similar term or a related term is a chemical equation. And a chemical equation is defined as a statement that chemists use to represent chemical reactions. Now, within chemical equations, we have two main components of the equation. The first of these components is known as the reactants, and they are the starting substances. The second main component is known as the products, and these are the substances that are formed in a chemical reaction. Now, another main component found in a chemical equation is an arrow, and an arrow represents the term yield, and it also shows the progression of a chemical reaction actually happening. Again, this arrow, what it means, what it represents, is that it's saying these components, the starting stuff, the reactants, are reacting to producing or they are yielding. And on the left side of the arrow is or are the reactants. And on the right side, that is going to contain the products. Now, something else in a chemical equation that is seen is when we have two or more reactants or products, what happens to represent or to separate those things out, we use a plus sign to separate out the multiple reactants or multiple products on one particular side of that arrow. So again, here I squeeze this in, but a plus sign separates multiple products or reactants on the same side. So it represents or it distinguishes between the multiple things that we have. So now that we have an idea again of what a chemical reaction, what a chemical equation is, we can shift our gears to how would we balance a chemical equation that we may come across in chemistry. So what we're going to shift gears to is the steps to balance that chemical equation. The first step to balance a chemical equation is to write down the correct formulas of our products and reactants involved in the particular equation. So this step involves using the naming protocol for ionic compounds, covalent compounds, and acids. Then the second step is to pick any element in the reactant side of the equation and determine the number of atoms you have for that particular element. The third step is to look at the product side of the equation for that same atom that you just did in step 2 here and determine how many atoms there are of that particular atom on the product side. The fourth step is to place coefficients, which those are those numbers out in front of either the product or reaction side to be able to achieve or obtain the same number of atoms for that same element on both sides of the equation. The fifth step is to repeat steps 1 through 4 until all atoms are balanced in the chemical equation. That sixth step is to make sure that the coefficients are in the lowest possible ratio. And then that 7th and final step is to check your work in that chemical equation. All right, so now that we have those steps to be able to balance the chemical equations, what we're going to shift gears to is actually writing a chemical equation. And so I have 3 examples that we will go over. So the first example here, it says in water, iron 3 chloride reacts with sodium hydroxide and produces solid iron 3 hydroxide and sodium chloride. So the first thing that we want to do is we want to write our formulas for our reactants and products. So we start out here with the first thing that's listed, and that is iron 3 chloride. So if you get your periodic table out, you will find that the symbol for iron is Fe. So again, just to show you here, iron has the symbol of Fe. So we write down Fe, and then we need to identify the charge. Well, because iron 3 is a transition metal, that charge is represented in parentheses. So the charge of our iron 3 is a 3+. And then we have chloride. And we're not going to find chloride on the periodic table. We're going to find chlorine on the periodic table. So chlorine has the symbol of Cl. Now, if you remember back to the ion formula writing sheet, you could go through and identify, based on the group number, what the charge is. Or if you forget, you can always find it on this ion formula chart. And so the charge for chloride is Cl1-. And so all we do from here is we swoop over the charge number to represent the number of atoms. So we have Fe, and we just need one of them, so we don't write that down. And then we swoop over the charge 3+ to represent how many Cl's we need, and so we need Cl3. So that is our iron 3 chloride. Now it says here it reacts. So in other words, this react symbol is just another word for a plus sign. So after we've written our FeCl3, we just represent a plus sign to separate those things out on the chemical equation or on the reactant side. And now we get to sodium hydroxide. So sodium, again, if you look sodium up on the periodic table, sodium has a symbol of Na, and so I write Na down, and Na has a +1 charge. Now again, you can think of those groups how we did for the ion notes, or if you forget, we have this chart, and if you look up sodium here, it has a 1+ charge. So sodium has a 1+ charge. And then hydroxide, that is another polyatomic ion, so that means you're not going to find it on the periodic table. What you have to do, you have to look back on our sheet here, and you find hydroxide. Well, hydroxide has the formula OH, so I'm going to write that down on our sheet, OH, and so hydroxide, if you look close, it has a charge of 1-. So again, what I'm going to do is I'm going to crisscross the charge number to represent how many atoms of each particular ion I need. So over here, because I had a charge of 1, I need 1 Na. Again, we don't represent that. We just write down Na. And then I need 1 OH-. Now remember, OH- is a whole set, but the only time I need to put parentheses to represent that entire set is if I need 2 or more. Since I only need 1, I can just write down OH. And then you see here this sign that says produces. This right here, and I'm going to write above it, this is another word to represent draw that particular arrow. So I'm going to draw my arrow. And it says it produces solid iron 3 hydroxide So again, the symbol for iron was Fe. The charge, because it's a transition metal, is represented in our parentheses, so iron 3+, and then hydroxide. Hydroxide is the same polyatomic ion that we found before, and so it is OH minus. And that is a 1 minus. Now again, now that we have this, we can crisscross the charge number to represent how many ions we need for this particular compound. So over here, because the charge of OH minus is 1, we have Fe, or we need 1 Fe. Then we crisscross the charge number here, and we need 3 OH minuses. Now because OH minus is a polyatomic ion and we need multiple of them, when we put it down here, we have to put that whole chunk in parentheses because we need OH as a set and we need 3 of them. And that's really important when we come to balance. Now, our last particular product here is sodium chloride. So again, you see this and symbol, that's another representation of a plus. And sodium chloride, the symbol for sodium is Na. It has a 1+ charge, just like it did on the other side of the equation. And then chloride is represented by Cl, and it also has that 1- charge, just like it did on the other side of the equation. We crisscross the charge number to represent the subscript, and so Na, we need 1 of those. Again, if we need 1, we don't write anything. And then Cl, again, we swoop there, and we need 1 of those Cls. So now we've set up our equation, and what we need to do is we need to balance this particular equation. So it really is just a guess and check method, and so what you need to do is just start out with any element in our particular equation and start identifying what to do, or start identifying what subscript to place. So I'm lazy here. I start out with the first thing I see, and that is iron. I look here, how many irons are in my left side of the equation? And we only see 1. Remember, there's no subscript, so that means we can assume just 1. And so I have 1 over here. And on this side of the equation, I find Fe again, and I just have 1 represented on that. So right there, that's balanced. We're good to go. We can move on to our Cls. So Cl here, to the right of it, represents how many we have. That means we have 3 Cl ions. Over here, we find Cl. There's nothing written. That means we have 1. So what we must do is this. We must place a coefficient to multiply something by 1 to represent 3. Again, something by 1 to get to 3. What we need to do is we need to put a 3 coefficient. So that 3 coefficient, notice how I did not affect any numbers out here to the right. All I did is I put a big coefficient out in front. This also applies to our Na and our Cl. So right now on this side we have 3 Nas and we have 3 Cls. And so that's our next problem here. Na, or our next atom. Na, we have 1 of these on our left, and on our right we have 3 times the subscript, which is 1. So 3 times 1, that means we have 3 sodiums. Again, the only way we can get additional sodiums is by placing a 3 coefficient. So again, that represents 3 times 1 as our 3 Nas. Now what this 3 also does is it applies that to 3 times 1, so 3 O's and 3 H's as well. So we move on here. 3 times 1 is still 3, so that means we have 3 oxygens over here, and we got to be careful. So notice how we put OH in parentheses, and then out to the bottom right, we put that 3. That 3 not only applies to the H, but it also applies to that O. So right here we have 3 times 1, which 3 times 1 represents we have 3 oxygens. So because we have 3 oxygens on the left and 3 oxygens on the right, the oxygens are balanced. And then what we do here is we do the same thing for hydrogen. So we have 3 times 1 hydrogen, and that means we have a total of 3. And then over here, again, because this whole OH minus is in a parentheses, this subscript applies to both the O and the H. So this becomes 3 times 1. We now have 3 hydrogens. Now, at this point, it is balanced. But what I want you to get in the habit of is I need to go back and double check to make sure I have equal atoms on the left side as I do on the right side. So always double check. And we'll have a couple more examples to go through this particular process. So we move down here to our second example. And our second example says liquid carbon disulfide reacts with oxygen gas and it produces carbon dioxide gas and sulfur dioxide gas. So we're throwing covalent naming this time into this particular equation. So we start out with carbon disulfide. And so carbon we can find on the periodic table, and carbon has the symbol of C. And so first thing we do is write down the symbol for carbon, which is C, and then disulfide. Di is a prefix. So we're not going to find sulfide on the periodic table, but what we'll find is sulfur. So sulfur is represented by an S. And then what's really nice about covalent compounds is that the prefix out in front here represents how many of that particular compound or how many of that atom we have. And so if you look back on your prefix chart from the prefix covalent compounds, you notice the prefix di represents 2 atoms. So for our sulfur, we need to have 2 or a subscript of 2 to represent that di. Now carbon does not have a prefix. So remember our one exception, and that is this: the first element listed, if there's only one, we do not put that mono prefix. So again, most of the time mono would represent 1, but because carbon is that first element listed, there is no carbon or no mono prefix. So our formula for carbon disulfide just becomes CS2. And I'm going to write that below here. So again, we see this reacts with, and reacts is just a fancy way to put a plus sign. And it reacts with oxygen gas. Now, oxygen, if we find it on the periodic table, it is O. Except there is one major exception. And that major exception is that these elements that I'm about to show you are called diatomic elements. So they make a nice 7, and so for this, they make a nice 7. So these 7 elements that I've just identified with you got to be careful here because it's these block plus H for hydrogen. If you see any of these elements that are just listed by themselves, so if it says hydrogen or nitrogen or oxygen, these things are known as diatomic elements. So again, what I highlighted in blue or boxed in blue, these are diatomic elements. And so what that means for us is that if they are ever by themselves or listed such as oxygen, they can't just be written with one O or one N. They have to be written with a subscript of 2. So our example here, oxygen, would have the symbol O, but because it's one of these 7 elements, it is diatomic. So we have to represent or put that subscript 2. So that becomes our symbol for oxygen gas. And so that reacts with, I should have put that earlier, but that's our plus sign. And then we have O2 as our oxygen gas. Because it's diatomic, we have to represent it as O2. Now then it says produces, which is a fancy word for draw that arrow, that reaction arrow, to distinguish the products from reactants. And now we have carbon dioxide gas. And so carbon dioxide is represented with a C, and then you're not going to find dioxide on the periodic table. You're going to find oxygen, and so the symbol for oxygen again is O. And then we have these prefixes. Remember the prefix from the previous part of this problem, di, represents 2, so that means we need 2 oxygens. And then again, we do not see a prefix in front of carbon. Now typically we would with these type of compounds, but because carbon is the first element listed and we only have one of those particular atoms, they do not use that mono prefix. So carbon dioxide, the formula for that becomes CO2. And then we see this and, which is another symbol or another representation for put a plus sign. And we have sulfur dioxide gas. So again, sulfur, just like we saw in the first part of the problem, represents with S. And then you're not going to find dioxide, but you are going to find oxygen. And then we see that prefix di. So the prefix di represents that we have to have 2 of those oxygens. And then no prefix for sulfur. Again, because it's the first element listed, we do not use that mono prefix. That means we just have one of those S's. So now that we have the products and the reactants for this equation, we can go and we can balance it. So again, you start out and you pick any element. And so I'm lazy, I start on the left-hand side. I see carbon. And so carbon, there is no subscript written here. I only have 1 carbon. Over here on the right, I find carbon again. Again, no subscript. That means I have 1. Those are balanced. We can move on here to our sulfurs. For CS2, you see there's a 2 to the right of sulfur. That means I have 2 sulfurs. I find sulfur on the right-hand side, and I have no subscript, so that means I have 1. So I got to multiply something out in front by 1 to get to a total of 2. So what I do, I add a coefficient. And again, notice how I do not affect these little numbers to the right. I always add a coefficient. So now I have 2 sulfurs, and I can move on to oxygen. So oxygen over here, I have a 2 as my subscript. That means I have 2 oxygens. And now we have to be really careful. Notice here on the right-hand side, we have CO2 and SO2. So we have to account for oxygen in both of those locations. Again, I had 2 on the left-hand side, but on the right-hand side, for CO2, that 2 is tagged along with the oxygen. So that means there's 2 oxygen from here, plus 2 times the subscript of 2 here, which is 4. That means I have 4 oxygen plus 2, a total of 6 oxygens. Now, I only have 2 oxygens on that left-hand side, so we have to think, what times 2 would get us equal to a total of 6? And the answer, to put that out in front, the coefficient, is 3. So I have to take 3 times 2 to get 6 oxygens, and that is equal to that 2 plus 4 oxygens. So right now, again, always double check your work, but right now that equation is balanced. So what we have, one more example here, and we will balance that particular equation here. So we'll shift gears and we'll balance our third and final example. So here we have solid zinc and aqueous hydrogen sulfate react to produce hydrogen gas and aqueous zinc sulfate. So we start out here with solid zinc, if you see an element listed by itself, again, we look to the periodic table of elements, we find that element, and the element zinc has the symbol of Zn. Now, something I want you to get in the habit of is always double checking. Whenever you just find an element by itself or it's listed by itself, double check and make sure it's not one of those 7 that we have identified. It is not, so we can just have zinc as a standalone element. It is not diatomic, and so we have Zn. And then we have aqueous hydrogen sulfate. And so, again, we see this and sign, so that represents a plus sign to separate these two reactants out. And we have hydrogen sulfate. Now, this is a compound, and it does have a particular charge associated with it. So we first find hydrogen. That is on the periodic table, and hydrogen is over here. It's H, and yes, it is boxed in, but we only do H2 if it's by itself. Notice how hydrogen here is involved in a compound. So if that's the case, we have to identify the charge for H+. And so the charge for H+, if you want to look it up, the charge is a 1+. So that represents our charge. So we have H with a 1+. Now sulfate. You can search all over the periodic table, but you're not going to find sulfate on the particular periodic table. You are going to have to find it on our ion formula chart. And so sulfate, if you look here, sulfate has a charge or has a formula of SO4 and a charge of 2-. So again, SO4, charge of 2-. So to get this particular formula, what we do is we take the charge number, we swoop it over. This means, because we had a charge of 2-, that we need H2. So we have H2. Now the charge for H+ comes over and swoops over, and this means we have 1 SO4. Now, we don't need parentheses because we only need parentheses in this type of polyatomic ion if we need 2 or more. So because we just need 1, all we do is we write down SO4. So hydrogen sulfate, the formula for that is H2SO4. Now, this says it reacts to produce. Again, produce is a big signal that we have to have that arrow. And so we draw that arrow to distinguish the reactants from the products, and we go from there. It says it produces hydrogen gas. So hydrogen, we looked up from the last time, it is H, it is by itself. And when an element is by itself, always get in the habit of checking if we have a diatomic element. Well, you look here, H by itself is boxed in. That means we can't just have H, we have to have H2. And so this becomes H2. And then you see the and, which is a fancy word for putting a plus sign. So we put that plus sign, and then it says zinc sulfate. So symbol for zinc is still Zn, and then we have sulfate, which is the same thing that we looked up here. So it's SO4, and its charge is 2-. So now what we have to do before we can put that formula down is we have to look up what is the charge of zinc. And it is a transition metal, but remember, it is one of those exceptions that does not have the charge written in parentheses. And so if we look here, we have zinc that has a 2+ charge. So we go ahead and we write this down as 2+. Now what we do is we swoop the charge numbers to become our subscripts. So that means because we have a charge of 2- on SO4, we need zinc, and I'm going to write this below because you'll see here in a second. Then we have a charge of 2+, that means we need 2 SO4s. So in this case, we need 2 SO4s. Now, and this will make more sense, notice here, I have zinc 2, SO4 2. What can we do with these 2's that are involved in the formula? We can cancel them out. So what happens here is this will become a 1, which we don't write, and this will become a 1. And we only simplify if charges are involved. So only ionic compounds. So zinc sulfate, the formula for that becomes ZnSO4. All right, so now we've gotten the reactants and we got the products, and we can just balance. So what we do here is this. We look and we find zinc. Well, zinc, there's no subscripts. That means we just have 1. We find zinc over here. Again, no subscript next to zinc. That means we just have 1. We find H. There's a 2, so that means we have H2. Over here we have H2, so that is good to go. Our sulfurs, we have 1s because there's no subscript. Over here we have 1s because there's no subscript. So S is balanced. We move on to our oxygens. Oxygen, there's a 4 represented here with that small number, the subscript. And over here there is 4. So that's our last element, our last atom that we have to deal with. And so right there, because we did all our work getting our reactants and products figured out, this problem is balanced. Again, I always encourage you to go back and double check to make sure that you have equal atoms on the left and right hand side, but this particular equation is balanced and we do not put any subscript. All right, well, I hope you have enjoyed this episode of Science with Surbeck, and as always, subscribe.